Okay, class, let me know, am I audible or not? Class, am I audible? Let me know. Okay, in the previous class, we have completed the analysis of slab culvert. We have calculated total design shear force, and after that, we have calculated total design ultimate shear force, and we have also calculated total design ultimate moment. So this is how we have analyzed the slab culvert. After analysis, we need to speak about the design. We need to design the slab culvert. Okay. So first, I will show you. This is total design bending moment, and that is 185 kilonewton meter. Then we have calculated total design ultimate moment, and we are getting it as 267 kilonewton meter. Total design ultimate moment is given by IS 112. In that code, the factor of factor of safety for the dead load moment is 1.35, and factor of safety for the live load bending moment is 1.5. And in total design ultimate moment, you're getting it at 267. Then after this, you have calculated the shear force, dead load shear force, and the live load shear force. For the shear force, the intensity of the load will be different. And we have seen how, okay. So we have calculated total design shear force, and after that we have calculated total design ultimate shear force. So now we will move towards the design of deck slab. Design of deck slab. Okay, so I will write here design of deck slab. In the slab culvert, see, this is the slab culvert that you have. It is supported on two bearings, and this slab is also known as deck. Since we have gotten the bending moment and the shear force for the slab, we can design the slab. Okay. Design of deck slab. Deck slab. Okay. So the grade of concrete that we are required to use is M25, that is given in the problem, and the grade of steel that is given in the problem is Fe415. So using M25 grade concrete, and Fe415 Fe415. So these are the materials that is given in the problem statement. For Fe415, you know the MULIN. MULIN depends on the grade of steel. So for Fe250, the MULIN will be different. For Fe415, the MULIN will be different. For Fe415, the MULIN is 0.138 FCK BD square. So from this formula, you have to check the required depth. How much depth is required for the cylinder? Already you have provided the depth. You have provided the overall depth. You have provided the effective depth. Now you need to check whether whatever depth is provided, is it safe or not? Is it safe against the strength or not? So we will check depth required. The formula will be modified as mu divided by 0.138 FCK B FCK B. Okay. So MULIN can be taken as mu. And what is mu? Mu is the ultimate design moment. And in the previous class, we have calculated the ultimate design moment. That is equal to 267. 267 into 10 to the power 6. We are converting that into Newton mm. Okay. 0.138 FCK is 25 and B the lateral dimension of the slab, the lateral dimension of the deck. So in the analysis and the design of the slab, whenever you are designing the slab, you are considering 1 meter width of the slab. So similarly here also we will consider 1 meter deck or 1 meter width of the slab. So B will be 1000. B will be 1000. So when you solve this, the D required will be equal to D required will be equal to 278. So this is the required effective depth of the deck. And what effective depth you have provided? The provided effective depth is 450 mm. Now you can say that whatever depth we have provided, it is safe against the strength. It is safe against the bending moment. This is the required depth and this is the depth that you have provided. Directly we can move towards the reinforcement. We will find the main reinforcement. Main reinforcement is related to the ultimate design bending moment. Okay. So for that bending moment, what reinforcement you are getting, you need to calculate that. So AST equal to 0.5 FCK divided by FY 1 minus 4.59 mu divided by FCK BD square. FCK BD square. So this formula already you have learned in the TRCF, in LSM, in your DDRCF, and even in your ADRCF. So you are very much aware of this formula. So we will use this formula to find the area of reinforcement required in the bridge. So our bridge is RCC bridge and we need to find the steel for the RCC bridge. Okay. So AHC equal to 0.5, FCK is 25, FY is 415, 1 minus under root 1 minus 4.59 into 267 into 10 to the power 6 divided by 25 into 1000 into 450. Okay. So you have substituted all the terms in the formula. You just have to calculate and the ASC will be 1758 mm square. Okay. Now you need to assume the diameter of the bar. This is the main reinforcement that we have gotten. For the main reinforcement, we will provide the main bar. So I will using 20 mm diameter bar, 20 mm diameter bar. Spacing, you know how to find the spacing? Spacing equal to width of the slab equal to area of one bar divided by ASC. So this is how you are calculating spacing in the slab. 1000 into 5 by 4 into 20 square divided by 1758. 1758 and that is equal to 178.6 mm. So this is the spacing that you are getting, but this spacing cannot be provided because this is not the regular figure. The figure has to be regular when you are providing the detailing. When you are providing the reinforcement, the figure has to be regular. To provide less than this, you can provide 150 mm. It should not be more than. So spacing, whatever spacing you have gotten, and you're, providing some spacing, that spacing should be less than this value. Provide 20 mm bar at the rate 150 mm center to center. Okay. And this is the main bar that we have gotten. This is the main bar. See, this is your slab, or you can say deck in case of bridge, and you have gotten the main bar. And the main bar will be provided along the length of the slab. And since you have analyzed the slab, you may also noted that it is one-way slab. The deck slab is one-way slab, and the main reinforcement will be provided along the length direction. Along the length direction, because the length is smaller than the width. If you see, the length will be the smaller than the width. So the main bar will be provided along the shorter direction, along the length. Okay, width is more than length here. We have seen the cross section of the bridge in the previous class. You can see the recording. Okay, so we have gotten the main bar, and here along the transverse direction, along the lateral direction, you will have the distribution bar. You will have the distribution bar. For the distribution bar, the bending moment will be different. You have provided the main bar for the bending moment 267, that is the ultimate bending moment. Okay. But for the distribution bar, the bending moment will be different. So 112 IS code 11, sorry, not IS code, IRC 11 code has provided the formula to calculate the distribution steel in the bridge in case of culvert. Okay. So distribution reinforcement shall be provided according to transverse reinforcement. Sorry, according to transverse moment shall be provided according to the transverse moment. And how to calculate transverse moment? Transverse moment means lateral moment. The moment in the width direction. The moment in the length direction we have calculated. The moment in the width direction, how to calculate that? It is given in IRC 112. Sometimes I will tell you the page number. I don't remember the page number. Okay. So I will give you the formula. This is moment. Transverse moment uh, equal to 0.3 bending moment, ultimate live load bending moment, okay, plus 0.2 NUD. See, what is U? U is ultimate moment, ultimate live load bending moment. NUL is ultimate live load bending moment, and NUD is ultimate dead load bending moment. So, you have to go back to the calculation of the bending moment. So here, MUL equal to, so what live load bending moment you have gotten? 113. Live load bending moment is 113, and it has to be multiplied by 1.5 factors, because 112 says that for the live load bending moment, the factor is 1.5. So you're getting ultimate live load bending moment as 169.5 kilonewton meter. Okay. And MUD, ultimate dead load bending moment. So what dead load bending moment you have gotten? If you see the previous recording, so that is 72 into IRC 112 says that for the dead load bending moment, the factor will be taken as 1.35. Okay, equal to 97.2. So these two values you can substitute in this equation, and you will get the transverse bending moment. You get the transverse bending moment. transverse bending moment, transverse bending moment equal to 0.3 into 169.5 plus 0.2 into 97.2. So this is equal to 71 kilonewton meter. The transverse moment will be very less as compared to the moment in the length direction. In the length direction, what moment we have gotten? In the length direction, we have gotten the moment 267 kilonewton meter. So for the transverse bending moment, you have to provide the reinforcement ASP, and ASP here it will be called as ASP for transverse bending moment. Okay, so that will be the same formula you have to use. Whatever the formula you have used for the main reinforcement, the same formula you have to use for the transverse. Okay, so this is 0.5 into 25 divided by 415 in the bracket 1 minus under root 1 minus 4.59 into mu. Here mu is 71. 71 into 10 to the power 6. Because we are converting, in the formula we are converting moment in Newton mm. Here it is in kilonewton meter and here it is Newton mm. That's why 10 to the power 6 is coming. Okay, this is 25. 25 into 1000 into 450 square. Okay. ASP in the transverse direction, we are getting ASP equal to 443.52 mm square. Okay, so this is the area of reinforcement that you are getting in the transverse direction. But you know, this since it is slab, the deck is slab. So we also have to check whether the reinforcement is more than the minimum required or not. And you know, what is the minimum reinforcement in the slab as per IS code IS 456-2000? The minimum reinforcement in the slab is ASC minimum. Can anyone tell me what is the minimum reinforcement in the slab? For SE415, for XYSD bar, the minimum reinforcement in the slab is 0.12% of B into capital D. For SE250, it is 0.15%. For XYSD bar, in the XYSD bars, SE415 is coming and SE500 is coming. So for XYSD bar, the minimum reinforcement in the slab is 0.12% of B into capital D. Okay. So 0.12% divided by 100 into 1000, B is 1000 mm into capital D is 500. We're not, taking small d, we're taking capital D in this formula. Okay, so this is coming as 600 mm square. So the ASC that you have calculated for the transverse reinforcement, it is less than the minimum ASC required. So you cannot provide this. You have to go for the minimum reinforcement in the lab. Okay. And with respect to this reinforcement, you have to provide the transverse reinforcement. So I will, I will provide 12 mm transverse bar. Provide 12 mm bar at the rate spacing I will take spacing equal to 1000 into 5 by 4 into 12 square divided by 600. The spacing is coming as 188.52 mm. Okay. But I can provide 180 mm less than that. So I will go for provide 12 mm bar at the rate 180 mm, 180 mm center to center. Okay, so this is what you can provide. Now the next step is That is very important, and that required to use the IRC code. The next step here is I'll give you the formula and I will also give you the page number where to refer in IRC 112. Okay, so the next step is check for ultimate shear strength. Check for ultimate shear strength. Any question? What happened? Any question you have? Ultimate shear strength. So to get the formula of ultimate shear strength, you need to refer IRC 112 2020 page number 70. Page number 70. Okay. In the page number 70, this has given the formula of ultimate shear strength. The page number 70. So I will write the entire formula and I will tell you what component you have to take and what component you can neglect. So this is given as VRDC in the code equal to 0.12 K bracket 80 rho 1 FTK bracket close 0.33, okay, plus 0.15 sigma CC bracket close into dWd. So this is the formula they have given in IRC 112 for the ultimate shear strength. And in the formula, this part can be neglected. So this part is related to axial force for the member. This part is related for axial force, and since we do not have the axial force for the slab culvert, we can neglect this part, 0.15 sigma CP. We can neglect that. Okay. So when you are neglecting it, you are only considering the vertical forces. If you have the axial force, then you have to take this. You cannot neglect. Since we do not have axial force in our member, we are neglecting it. Okay, so the formula will be modified as 0.12 K bracket 80 rho 1 FTK bracket close. The bracket is raised to 0.33. Then again it is closed multiplied by dW into D. I will tell you what is K, what is rho, and what are the other terms I will tell you. Okay, I will pause for some time. Okay, so we are back. Uh, K is given as K equal to 1 plus under root 200 divided by D, and it has to be less than equal to 2. Okay, so you can substitute the value of small d. Small d in our case is 450. 1 plus under root 200 divided by 450. Okay. So this is coming as 1.66, which is less than 2, and this value can be taken. So we have gotten the value of k. Now we will see what is rho 1. We know x is k, okay? Now we will see what is rho 1. Rho 1 is, rho 1, all the formulas are given in IRC 112. Rho 1 equal to AST provided in the longitudinal direction. AST provided in the longitudinal direction divided by BW into D. And this has to be less than equal to 0.02. So, you know what AST you have provided in the longitudinal direction. So I will, you know how to calculate that, but I will directly write the value here. You know how to calculate. If you don't know, we will see in the next class. So what AST you have provided? You have provided 20 bar at the rate 150 center to center. So that has to be converted into AST. That spacing and that bar has to be converted into AST. See, this formula is spacing equal to sorry, spacing equal to 1000 into small AST divided by capital AST. Okay. So small AST is, area of one bar. That is area of the 20 bar. 1000 is the width of the slab that is considered, and spacing that we have provided is 150. So you can find AST. So directly I will write here AST equal to 2094 divided by BW. Again, it is the width of the slab, 1000 into small d is 450. Okay. So this is coming as equal to, this is coming as 0.0046, which is less than 0.002, and this value can be considered. Okay. Okay. So we will use this VRDC formula because we have gotten all the terms in the formula. We use the formula and we will calculate VRDC. VRDC, what is VRDC? Ultimate shear strength for the deck slab. VRDC equal to 0.12 into K is 1.66 into bracket 80 into rho 1. What is the value of the rho 1 we have gotten? Value of the rho 1 is 0.0046. Okay, into 25, bracket close, raised to 0.33, raised to 0.33, okay, into BW. Again, the bracket, entire bracket is closed, into BW is 1000, okay, and into D. D is 450, small d is 450. Okay. So by solving this, the VRDC that you are getting, VRDC equal to 188 kilonewton. So after calculating the VRDC, it has to be bigger ultimate design shear that you have calculated in the analysis. You see, go back to the recording. So the value of ultimate shear, ultimate design shear is 169 kilonewton. And the ultimate shear strength is 188. So the strength is greater than the design shear. So it is safe. When it is greater than the design shear, then it is safe. Otherwise, you need to change the depth of the slab. You need to increase the depth of the slab. When you increase the depth of the slab, this value will be greater than this. Okay. So this is what we have calculated. Now we will see the detailing of the deck slab. That is the last part that we will see. So it is just like a slab. Deck is like this. And it is having the bearing. The dimension of the bearing is, I think it is 450. I don't remember, you see the recording. It is 450. So in the longitudinal direction, we have calculated the reinforcement. In the length direction, sorry, in the length direction, it is 20 mm bar at the rate 150 mm center to center. Okay. Now we need to provide the distribution bar. So the distribution bar will be here. Distribution bar. It will also be provided in the top distribution bar and also provided along the transfer direction in the top. So all those are in the red color are the distribution bar. Okay. So what distribution bar we have provided? 12 mm at the rate 180 mm center to center. Here also we have provided distribution bar, which is 12 mm at the rate 180 mm center to center. Okay. Okay. So this is the detailing of the deck slab that we are done. Okay. 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 So you have any question you can ask? You have completed the design of the culvert. Again, you go back to the recording, see all the videos, and you will learn this. Again, this video is also recorded. I will upload this in the drive. Any question, Hasir? Any question you have? Hasir? Hello? I'm audible?
Yes,
Yes,
sir.
sir.
Hasir, where are you? Hasir is not replying. Okay, no issue. So we have completed the design of the slab culvert. From the next class, we will see, design of girder
Okay, sir.
from tomorrow. Okay, thank you very much.
Thank you, sir.
Okay, sir. Thank you.